Hello, I'm Hannah Critchlow reporting from Calcutta, India, for this special edition of Naked Neuroscience, in which I took to the skies, travelling 5,000 miles southeast from London to descend off the Bay of Bengal in Calcutta, a hot, chaotic, sprawling city that's home to at least 15 million people. In the previous episode, we met Robin Sengupta, a man who, inspired by what he saw whilst working for over 50 years in the UK National Health Service, raised millions of pounds to set up a 10-storey neuroscience hospital and research facility back in his homeland of India. His school friend had this to say.
People here in Calcutta think him as a god. He's so pious man, a religious man. He's like a god.
In this episode, we continue our journey, taking to the hospital wards to discover how Botox, one of the deadliest toxins ever discovered by humans and found in gone-off sausages, helps iron out wrinkles and treats people afflicted by uncontrollable tremors.
As she's contracting her jaw, I can hear the sound that I'm very clear that the needle is inside the jaw.
Plus, we'll find out how UK and Indian scientists are joining forces to keep human brain tissue alive in a petri dish in the hope of developing a new treatment for epilepsy. All to come. First up, I went to speak with the son of one of the patients being treated in this 150-bed hospital.
His name is Vishwaranjan Nyogi and he is 49 years old. He got brain tumor. Previously, it was operated. Again, it came and it has to be operated tomorrow. It is malignant glioma tumor.
So it's malignant, so cancerous growth on the left-hand side of his skull. And you can see above his ear there is a slight lump there, a slight swelling.
Yeah, this lump. Sometimes he forgets names of anything. Second thing is his right side is getting paralyzed. He's getting fall every time.
To find out more, I spoke with his attending doctor, Shoptu Shibasu.
Mr. Vishwaranjan Nyogi was admitted with difficulty in orientation to time, space and person, and difficulty in walking and disbalance.
So in November last year, he had surgery to remove a malignant tumour that was on the left side of his brain, kind of just above his ear.
Yeah, so it was a gross total excision of the tumour that took place, and he had radiotherapy and chemotherapy. This is the case. It's a tough case, tough operation. So we're monitoring him and seeing how he's maintaining his vital statistics.
So the cancer has grown back, and then tomorrow he's going to be operated on to remove further of them.
Will be again, the tumour has grown up, and so we will be operating the rest of the residual tumour which is left. Let's see how things go. So hopefully he will do good.
And his wife mentioned that she was concerned that the tumour would come back again after the operation tomorrow. What chances of success do you think that you have?
Success, definitely we have a good success rate, but depending upon the tumour, it varies, and so it varies from patient to patient.
So the tumour tissue will be removed during the surgery. But what happens to this sliced out section of human brain? Is it burnt or put in the bin? This patient has decided to donate it to research. I spoke with his family about the decision.
Yes, we are happy. If it will help to make any prevention or any kind of further medical science progress, that maybe help other patients, maybe not for him, but that will help other come out of this problem.
I left them all to prepare for the next day's surgery. And the following day, whilst Vishwaranjan Nyogi's operation was coming to a successful close, I met with Dr. Mark Cunningham. He set up a laboratory, shipping over equipment from the UK and putting it together a few floors above the surgical unit at the Neuroscience Institute, Kolkata. He had just received the patient's brain tissue.
We've got the sample in the bath on the vibratome, and the noise you can hear is the vibratome cutting through the tissue, and we're currently cutting slices of a thickness of less than 0.5 millimetre. That value is critical for two reasons, really. It preserves enough of the neuronal microcircuitry so we can keep the tissue alive. It also is thin enough so that you can actually get oxygen and the various ions that the tissue actually needs to be kept alive as well.
And how big is the chunk of tissue that's been taken out during the surgery?
So it's probably about 5 millimetres cubed. It's quite a small bit of tissue, and it's from the peritumoral zone, so it's around a tumour. And this is thought to be the critical part that causes seizures to arise in particular types of central nervous system tumours.
And so the patient was having epileptic seizures as a result of this tumour that was growing on the side of his head?
That's right, yeah. So in these particular types of gliomas, there's a high risk of seizures, and in many cases the seizures are one of the ways in which these tumours will actually present. So usually the patient has a seizure, and they then go for a subsequent brain scan, MRI, and lo and behold, you usually find a glioma in the scan.
And the tissue looks a little bit like sushi, to be honest with you.
Well, I frequently try and describe to people as like a little blob of chewing gum. You can clearly see the white matter here, and then above the white matter you've got the full cortical thickness, so this is the grey matter above here, and that's where all of the neurons are, and that's the part of the tissue that's actually generating the seizure-like activity.
The grey matter bit, and it's actually not really grey, it's kind of more pinkish.
Yes, well, obviously this has been removed, so there's going to be some blood vessels in there as well, and those give it that slightly pink hue. So you've got intact small vessels, which up until the moment the tissue was removed was still supplying it with oxygen and with energy. And so what we try and do is essentially recapitulate to a certain degree that physiological condition using a specialised in vitro brain slice chamber, which means that the tissue will be kept healthy and therefore viable for us to do electrophysiological recordings.
And the vibratrome slicing through the chunk of tissue now, and we've just got our final slice, so the 10th slice of tissue. And the vibratrome looks a little bit like a guillotine, actually, that's chopping kind of through the tissue, vibrating at quite a high frequency.
80 hertz. So it's vibrating at 80 hertz. It's moving at a speed of 0.2 millimetres per second and an amplitude of the movement of the blade of about 1.5 millimetres. The way that I sometimes describe it to my friends who are non-scientists is most of us can recall in the good old days when we used to go to the deli to get a couple of slices of ham, and the butcher or the man behind the deli counter would have this device which would allow him to slice through the ham. This is sort of a much more sophisticated version of that.
We'll return to Mark's experiment later in the show, and we'll also explore exactly why these Newcastle researchers are setting up experiments in India.
The axis of power in terms of biomedical research is definitely moving eastwards. I believe very strongly that we in the UK should be working with India, if only so that the UK can stay in the game, and so that India is not left behind by powers of China.
But first, I took a lift downstairs to the clinic. Where Dr. Kumar was poised with a needle full of Botox to help one of his patients, who was called
Sanju Sharma. And the problem she has is for last few months, she's having difficulty in opening mouth, and she's involuntary closure of mouth. So without her control, mouth is being closed. So because of that, she has tongue bites, and it's quite inconvenient. You can see her neck. There's some contraction of the neck also. So she keeps on moving the facial muscle and the neck muscle. This condition is known as dystonia.
And you can see that the jaw is kind of collapsed and gone much smaller, and the mouth is very tight, but also quite saggy around the lips. And then the neck keeps on tensing up and moving.
The muscles which closes the jaw, that is contracting involuntarily. Mouth is all the time collapsed. So this is very important to give her functional benefit.
So being able to speak, for example.
So she can speak better, she can eat better. Because right now what's happening that she cannot put the morsels of food properly in the mouth because mouth doesn't open widely. She has taken various treatment. Dystonia can be treated by some medications also. The result is not very good. It's poor actually. So the Botox is the mainstream treatment of the dystonia.
So that's Botox that's usually used in cosmetic surgery to get rid of wrinkles, for example.
Exactly. Botox, whenever I say Botox to a patient, I don't want to go for cosmetic purpose by using Botox. But Botox has a lot of medical indications. That includes dystonia. That includes spasticity also. In a spastic child, you can use Botox. Nowadays, Botox can also be used for excessive salivation or drooling. So it has a lot of medical indication which people are not very much aware of.
And Dr. Kumar is now taking an injection of Botox and...
I'll palpate her facial jaw muscles to see that which muscle is stiff. There's a muscle over here known as masseter, which is a strong muscle at the side of the jaw. So what I will do, I like to inject Botox in this muscle. But what happens, this is a thin sheet of muscle. When you go for injection of masseter muscle, you may overshoot the muscle and you may inject in at some other area. So you need some guide for that. And that guide is the EMG, electromyogram machine, just to see that I'm right spot.
So the needle with the Botox in the syringe is also attached to an EMG machine which is measuring the electrical activity of the muscles contracting, kind of almost spasming as a result of the dystonia.
In this needle, the advantage is that once I'm inside, when I know that I'm inside the muscle, at the same time I can inject. So it has a portal for the injection also.
So Dr. Kumar is now probing the jaw and finding the muscles that are contracting.
This sound of crackling sound, that means I'm right muscle, contracting muscle. You can see.
And on the EMG screen, you can see spikes of electrical activity of the muscles are continually contracting.
Yeah. Now I'm very clear that I'm right muscle. I'll inject the Botox, the dose of what I decided, at the same place. If I have any confusion, I ask the patient to clench the jaw and hear the sound.
So her jaw is opening and there's no sound?
दांत जोर से दबाएं. As she's contracting her jaw, I can hear the sound. That I'm very clear that the needle is inside the jaw.
And is now pressing down on the plunger of the syringe and injecting, it looks like about 10 millilitres of Botox solution. And out comes the needle, and the EMG machine is silent. So what exactly is the Botox doing to the muscles and the nerves there?
Botox works in neuromuscular junction. It is not working on muscle or nerve, it's neuromuscular junction.
So that's the kind of the gap between the nerve endings and the beginning of the muscle.
Exactly. So when we have to do any activity, brain gives signals from the brain to spinal cord, to nerve, and this signal is transmitted to the muscle. So to transmit that signal, you have to go through the gap. Just before the gap, at the ending of nerve, there's a chemical is released. The name is acetylcholine. So once acetylcholine is out, it will cause contraction of muscle. What is happening in a case? More information is coming from the brain than required. So more electrical activity, more acetylcholine. So what Botox does, it reduces the secretion of acetylcholine from the nerve ending, so that muscle is not over-contracted.
And that's why it also works in plastic surgery in order to stop people being able to frown or even smile, causing contractions of their muscles.
Yeah. In cosmetics, whatever you see the wrinkles, actually they are activity of muscles. They're contracted muscles. The wrinkles on the forehead, the wrinkles on the cheek. So by Botox, you reduce that activity. That's why it becomes flat. You look younger. At the same time, if you want to smile, you can't smile properly because muscles are weak.
And how are you feeling after that injection?
कैसा लगा? दर्द तो नहीं हुआ ज़्यादा?
नहीं ज़्यादा नहीं हुआ.
So she's telling that it was not that much painful. It was minimally painful.
Thanks to Sanji Somar and Dr. Kumar. Next, I return to Mark's laboratory to find out what Bisho Yanyoga's brain slice was revealing.
So we're now recording from the slices that we cut earlier on. What we're doing is we're carrying out extracellular local field potential recordings.
So you've got the little brain slice in the recording chamber and an electrode is being stuck, or a few electrodes actually, are being stuck into the tissue, and you're recording the electrical activity around the brain tissue, so not in one particular nerve cell?
No, it's so the brain slice contains networks of neurons, networks of brain cells, and the particular type of recording that we are doing is we're using a glass micropipette, so a very small electrode, and we insert it into the brain slice, and we're recording the network activity. So the activity that is generated by tens of thousands of neurons around the tip of that electrode.
So we've got the trace here of, if you imagine a graph in which the y-axis, which points upwards to the sky, is measuring voltage, like electrical voltage in your house, and on the x-axis it's time in milliseconds. We're going to transform that voltage into a sound. So this is a standard nerve network with a tissue producing electricity. And now, Mark, you're adding a solution of something to the brain tissue.
Yes, so the peritumoral samples that we obtain, so this is derived from work that we've been doing in Newcastle. What we found is that in the brain slices that we get from these peritumoral regions, there's spontaneous interictal discharges. So these are ongoing events which are indicative of a bad bit of the brain, so a bit of the brain which has got a much lower threshold for these pathologically excitable events. And we, as I say, we can see these events spontaneously in this peritumoral tissue. So what we're trying to do now is we're trying to manipulate that brain slice to actually go from an interictal stage to an ictal stage. And an ictal stage is when you actually have a seizure. And why that's important is we're trying to understand the mechanisms that underlie the transition from the interictal stage to the ictal stage, and trying to then interfere with that change using various blockers to tell us something about the mechanisms that are involved in seizures associated with tumours.
So you're basically causing the brain tissue to have a brain seizure.
Yes.
And it sounds a little bit, if you get to transform the voltage into frequency of sound, then it will sound like this. And this is much better than doing these types of experiments in, for example, a mouse or a rat tissue.
Well, there are models of brain tumours using animal models. They have various problems associated with them. So some people might argue that they're not really indicative of the human condition. What you have to do is you have to take human glioma cells and then inject them into the brain of a mouse or a rat, and then the tumour grows and the mouse or rat then has a brain tumour. But it might be argued that that doesn't truly recapitulate what you see in human tumours. There are a wide variety of different tumours that can be graded due to their pathology, and one might argue that the type of tumour that's being modelled in a mouse brain is only one type of model, and one that is not associated to some extent with tumour-associated seizures.
And how long can you keep these human brain slices alive in this artificial kind of brain solution then, CSF solution?
As long as the slices are kept oxygenated and they're provided with the nutrients via the artificial cerebrospinal fluid. In our hands, we've been able to observe healthy slices for up to 20 hours. But one of the things that we would like to do is obviously extend that period of time. And we're now in Newcastle looking to explore culturing the slices to extend the life of the slice. And that will allow us to do lots of different experiments that require much longer epochs of time. There's been very few studies on trying to culture human tissue, and most of them have concentrated on looking at anatomical findings. But recently there was a report from a group in Paris that's now demonstrated that you can in fact culture adult human brain slices, and they were able to show that they could keep these slices alive and conduct electrophysiological experiments for up to 6 weeks. So it can be done. It's a question of modifying the existing approaches and optimizing them for adult tissue.
And then final question. Are there any other brain surgeries where you could get tissue, human brain tissue, in order to do experiments on?
Well, these samples all come from operations where the tumour and surrounding infiltrative zone are being removed. But we also obtain samples from patients who are undergoing mesial temporal lobe epilepsy and are having part of their brain called the hippocampus removed. And that's the type of work that we've been doing in Newcastle for about the last 6 or 7 years, and we've successfully demonstrated that we can record epileptic activity from tissue obtained from those patients as well.
All cutting-edge research. But why were Newcastle scientists coming all the way over to India to conduct this work? Was it easier to do here because ethical regulations are looser than in the UK? I posed this question to Mark Cunningham and his colleague Dr. Mark Baker, a Newcastle neurologist who was also working out here.
Well, I mean, ethics is uniform throughout the world. The Helsinki Declaration very clearly states the guidelines with respect to ethics. And as such, there is a stringent ethical procedure that we've had to go through for all of the projects that we are involved in here at the Institute of Neuroscience, Kolkata. The most fundamental point to make is that all patients undergo a process of informed consent, which is at the very heart of all ethics with respect to doing any research with patients.
And then in terms of patient numbers, Mark, you've been going through many patients with motor dysfunction today and testing their electrical responses in their muscles. And Mark, you're getting quite a lot of access to tissues. So is that one of the reasons that you're coming out here to India? Simply that you get larger numbers of patients to work with?
Of course, I mean, in terms of the numbers, as scientists, we're very much constrained by reproducing our findings. And whereas in the UK, you might have to wait 3 or 4 months to get a suitable number of repeated experiments, or Ns as we call them, here you would probably be able to do the same amount of work in a month.
To put it in perspective, the static population of Calcutta is probably somewhere between 12 and 15 million, which is twice as big as London. And the catchment area for the Institute of Neuroscience Calcutta not only encompasses the urban population of Calcutta, but rural populations and other urban populations within West Bengal. The advantage of having a single institution, a focus for all of the neurology in that catchment area, means that there are large numbers of patients coming through with various conditions. One other comment, and that is that the studies that Mark and I are collaborating on out here in Calcutta are identical to studies we're running in Newcastle, which have gone through the UK ethics process. So we're not doing anything different. It's just, these are projects that are up and running, and they're a nice way of introducing the science that we do to our collaborators out here in Calcutta, and ultimately give them the ability to take them on and take things further. And the advantage for us is that our numbers are increased. It's just a numbers game.
We also get to train the next generation of Indian neuroscientists and expose them to the techniques, the technology that we've taken out with us, and hopefully help in terms of training and development of those young neuroscientists.
The primary driver for us coming out to do experiments is really to set up facilities within the Institute of Neuroscience Calcutta that will enable the clinicians and scientists working at the Institute of Neuroscience Calcutta to have state-of-the-art technology at their fingertips to do state-of-the-art neuroscience. What we're doing is essentially providing equipment, training, and to some extent a service that allows us to work in collaboration with these people, and for our colleagues at the Institute of Neuroscience Calcutta to work independently to develop their own research streams.
And countries like India, for example, and Korea and Singapore emerging as having serious scientific competitive edges to, for example, the UK and Europe. What kind of influence will your educational training programme have on that?
So I agree. The axis of power in terms of biomedical research is definitely moving eastwards. I think the UK has a much greater history with India, and I believe very strongly that we in the UK should be working with India, if only so that the UK can stay in the game, and so that India is not left behind by powers of China and, as you say, smaller but more focused powers such as Singapore. imbalance in this region is not going to be helpful in the future.
Does it make a difference that 80% of the people that visit this institute are paying? They're effectively getting a business health service and they're paying for that treatment, and 20% of them aren't. So does that make a difference in terms of which people then elect to undergo these experiments with you or take part in the research with you?
If we're going on UK data, and this question has been asked of NHS patients, across the board, no matter what the social background, patients want to be involved in research. It's one of the priorities in the NHS. Patients are the same the world over. If someone is giving them the offer of participating in a research project which will benefit society, most people will say, yes, I'm in.
Thanks to Mark Baker and before that, Mark Cunningham from Newcastle University. And Bisho Yanyogi's brain surgery was, thankfully, a success. Over the last 2 episodes, we've explored how a remarkable man, Dr. Robin Sengupta, started his career as an 8-year-old boy, selling fruit in a bustling bazaar off the Bay of Bengal in order to help support his family. He borrowed school books from friends and studied at night, gained scholarships and eventually moved to the UK to work within the National Health System in Newcastle, working his way up to become a neurosurgeon. And inspired by the NHS, he raised millions of pounds to set up this 10-storey, 150-bed neuroscience specialisation hospital back in his hometown of Calcutta, India. The hospital offers free treatment for those who cannot afford it, and embedded within it a cutting-edge research facility and training ground for future neuroscientists. I asked one of his colleagues, who wanted to remain anonymous, what the reaction was back in the UK when Robin announced his grand vision over a decade ago.
I thought he was mad initially. To be honest, most people would think it wouldn't be possible, but if there's somebody who could make it happen, it would be Robin, because he's so demanding, and so, not demanding is the wrong word. He's so persistent, and he's got, lots of vision.
I also spoke with Robin's daughter, Anita, on what it was like to have Robin as her dad.
My recollection of him as a child was me forcing him to read all the famous 5 stories, and then I tested him on them, and he was very good. And he'd take us swimming and do things that a normal dad would do. I just got lifts everywhere I needed to. Usually he was quite embarrassing, which he still is, which is what most fathers are. But I think he was just an average dad, really. I mean, I know he was away at certain times for conferences and what have you, but we did live very close to the hospital. So I suspect that he'd come home at tea time and then maybe go back. Now that I'm a grown up, apparently, I can recognise the quality of his achievements, and they're outstanding. I mean, we're extremely proud of what he's done. I think the building is more of a physical representation of the achievement, and I think just seeing the staggering size of it and what it is and the people working is unbelievable. In fact, I'm not really sure I entirely believe it. Yeah, very proud and just really in awe of what he's done.
Well, that's all we have time for this month, I'm afraid. Thanks to all those who contributed to this special 2-part Indian Naked Neuroscience series. Robin Sengupta, Shoptushi Basu, His Excellency the President of India, Tushakandi Jogri Tuti, Babu, Bonashi, Rishi Kumar, Kovin Kumar, Alaknandat, Shoptishi Basu, Mark Cunningham and Mark Baker, Anita Sengupta, Bishu Yanyogi and Sanji Somar. Phew. See you next month to Open Our Minds, where I'll be back in the UK putting the brain on trial to uncover what power science actually has. We'll be exploring the influence of neuroscience in the courtrooms. The judicial system could be construed as the backbone of how our country operates, a constitutional pillar of our democracy. How does neuroscience shape this? We'll be finding out. My name's Hannah Critchlow.